Running Kubernetes locally is straightforward, but moving that setup into a live environment is where unprepared teams get burned. To survive that transition, we use this mind map. It outlines a proven 15-point checklist designed to harden a standard cluster into a production-ready environment. Once applied, this framework yields a system capable of intelligent scaling, automated recovery, and complete microservice visibility. To follow along with these steps, you need 3 prerequisites: an active cloud Kubernetes cluster, kube control access, and a blank Git repository. In a production environment, skipping even one of these foundational pillars leaves the system running on borrowed time. Readiness is a strict binary state. You are either fully prepared or you are waiting for a failure. We start with the first branch on the map, architecting for resilience. This illustrates the physical requirement, distributing your cluster across 3 availability zones to eliminate single points of failure. Within those zones, separate workloads. Create dedicated node pools for system tasks, distinct application pools for live services, and spot pools for batch jobs. Before assigning resources to these pools, you have to profile your applications. Failing to understand base memory usage before setting limits is the most common cause of out-of-memory, or killed pods. Look at this YAML snippet. Every pod must explicitly define CPU and memory requests and limits right here. Without these exact boundaries, the Kubernetes scheduler cannot make intelligent node placement decisions. Moving down the map, the second phase focuses on locking down security. Start by stripping away wide cluster admin rights from application service accounts. Replace them with granular, least privilege role-based access control, and enforce default deny network policies that block all traffic until explicitly allowed. Next, enforce strict pod security standards. Actively prohibit root containers. Mandate read-only file systems, preventing easy container modification. Another major vulnerability in standard setups is the use of plain text Kubernetes secrets. They are simply base 64 encoded, not encrypted, leaving sensitive data entirely exposed. The correct architecture routes encrypted secrets externally. On the right, you can see an external secrets operator safely pulling dynamic credentials directly from a vault like AWS Secrets Manager, bypassing plain text entirely. Because every file in your Git repository acts as a blueprint for the cluster, you must never commit unencrypted secrets to Git. One accidental push can expose your entire production credential stack. A multi-zone, highly available infrastructure offers no protection if an attacker can pivot through a single, overprivileged, insecure container. Following the map, we reach the third phase, full-stack observability. The baseline requirement here is pairing Prometheus with Grafana to monitor node resource limits and track request rate, errors, and duration. For logging, deploy an aggregator like FluentBit to collect and route all standard output and error streams into a centralized, searchable system. Tracing tags a single user request with a unique identifier as it hops between different containers, exposing hidden latency bottlenecks. With clear visibility established, we transition to the top of the fourth branch, operational reliability. You must configure liveness, readiness, and startup probes. The control plane relies entirely on these checks to know exactly when to route traffic to a container or when to terminate a hung process. Look at this cluster schematic. We use a horizontal pod autoscaler for traffic spikes, but pair it with pod disruption budgets. Notice how the budget actively blocks the termination of the final required application pods, even as a server node goes offline for draining. True system reliability is defined by the cluster autonomously identifying and mitigating degraded states before the end user ever notices an issue. We finish the checklist with 2 interrelated phases: automated GitOps deployment and disaster recovery. The core philosophy of GitOps tools like ArgoCD or Flux is straightforward. The Git repository serves as the sole source of truth for the entire cluster state. Because of this structure, any manual configuration changes made directly via kubectl will be immediately detected as drift and overwritten by the GitOps controller. The controller continuously syncs the live cluster to match the declared code in Git. Watch this interface pull a new deployment manifest, changing from a yellow out-of-sync warning directly to a green synced status. As your final backstops for disaster recovery, configure automated etcd database backups alongside persistent volume snapshots. Manual operations simply cannot scale under intense system pressure. Defining the infrastructure as code allows you to coordinate these backups and snapshots, enabling the cluster to be restored with precision and speed. Step by step, this infrastructure has evolved from a fragile development setup into a self-healing, auto-scaling production environment. This specific architecture blocks rogue deployments inherently, while providing deep X-ray visibility into network traffic and performance bottlenecks. You can see the stable state of the system reflected across the tooling stack, from pristine terminal outputs and green deployment dashboards to steady metrics charts. Check the description below to download the complete 15-point mind map and our boilerplate templates. Maintaining a production environment requires an ongoing discipline of continuous alignment, not a one-time script.